Hey, it's me again. Our next lesson is inverse trigonometric functions. Our mindset message for today is everyone's ideas are important. I didn't choose this in particular because of today's topic, but it's important to remember that. All of our ideas together form one way more powerful whole than any individual person's ideas. So that's always something that's important, but especially in mathematics. A lot of times we feel like I don't have something to give because maybe I feel like I'm not traditionally been one of these people in the math circle or something like that. But actually often you have more to give than you think because you may just think differently about things, and that can help everybody's understanding become more complete. Our learning goals for today, there's one main learning goal, and that is to define inverse functions for sine, cosine, and tangent. We are going to get some review with inverse functions and stuff as well. So our prior knowledge, of course, is what inverse functions are. I will post up resources to remind you all those facts about inverse functions. One particular thing about inverses that's important is to remember one-to-one functions. And usually we start studying and talking about one-to-one functions when we learn about exponential functions, because those are a great example of one-to-one. And remember, that means exactly one output for each input. If you recall, just a function doesn't have to be one-to-one. A great example is a parabola, because there's actually multiple inputs that could make the same output. But a one-to-one function is even further restricted because we're saying exactly one output for each input, no more, no less, and you cannot have multiple inputs that give the same output anymore. And then, of course, since we're using this in relation to our trigonometric ideas, then it's good to remember the sine, cosine, and tangent graphs for this lesson. Let's dive into an example of purely review here, actually. Important thing, though, I want to tell you, and this is big. Only one-to-one functions have an inverse function. Yes, this should have been something that you learned before when you learned about inverse functions, but I'm going to say it again, okay? And the good thing is, if it's not one-to-one, make it be. What that means is, if it's not one-to-one, maybe you can just chop the graph, and I like to think of the graph, but chop the domain so that just a piece of the function becomes one-to-one. And we'll talk about that in this context. So, first example, restrict the domain of f of x equals x plus 4 squared minus 1 so that it becomes one-to-one. And this is just the shorthand for one-to-one. All right? You recognize that this is a parabola, right? But its vertex has been shifted, yeah? So here's what I want you to do to get some practice right now first. I want you to pause, and I want you to find the inverse of this function. And then I also want you to graph this original function as well as its inverse. And again, if you need to review those things about inverse functions and their graphs, you can do that to help you complete this. So go ahead and pause right now. Okay, so important fact about inverses, remember, is that they represent the complete undoing of the other function. So whatever function this is, right, has to represent the reverse, exact reverse steps for this function. So if we step through the order here, if you were to plug a number in and do the order of operations, first we'd add 4, then we'd square, and then we'd minus 1. So how do I go backwards with that? Or here's what you could think of. You could think of if I actually took an output and I said, what if I want this to equal 10? How would you solve for x? That's exactly the way to find the inverse, right? So how would we solve for x if I had something here? I'd add 1, then I would square root, and then I would subtract 4. So this inverse function should take x, and it should add 1, then it should square root that, then it should subtract 4. All right? Now we can look at the graphs of those two things. Avoid confusion here. Let's use blue and orange to represent the separate graphs. Hopefully you recall that this is just a parabola shifted left 4 and down 1. So if I go back to negative 4, And then let's call this -1. My vertex is now right here, I believe. All right. And this would then go here. Now, this square root function, there's different ways we can view this. One thing I want you to remember about inverse functions is that inverse functions are always reflected across the line y equals x. You can also just think it swaps the x and y. It just swaps all the x's and all the y's. So this vertex is at -4, -1. Then if you switch that, it's going to be at -1, -4. So -1, -4 is, let's put this over here, is going to be the location of the other guy. But since it's been reflected across this diagonal line, it's going to be on its side, right? Now this is important to remember. This guy's reflection in this way is no longer a function, is it? And this gets back to what I actually asked in the first place. How would I restrict the domain of the original one to make it one-to-one? Because remember, right now, this is not one-to-one because you have these pairs all along here that have the same output as each other. But you know, it's one-to-one because of that symmetry. How do we eliminate that symmetry? Right? So we could simply chop one or the other of these off and restrict the domain. Okay? So this guy's current domain is all real numbers. But if I just chopped this off, I could have chosen the other side, but it's standard to choose the positive side, I guess. And by chopping that side off, that actually chops this underside off of this. One comment I should have made. When you solve this, actually, that would be a plus or minus. Remember when we undo squaring? And so we're actually, what we just did while erasing that was that we eliminated the minus and we only kept the positive part of the square root. So actually this guy's actual graph is just this. So to answer the original question then, let's actually state it out. -4 is this vertex, so I can keep everything from -4 and up, right? So the new restricted domain would be x greater than or equal to -4. Another way we put that is, I'll share with you a kind of notation that's maybe new to you, but sometimes with domain we express it, and I'll just say or, we can express it by saying -4 comma infinity. This just means from -4 all the way forever to infinity. And the reason these two brackets are different, if we have a hard bracket, that means include that number, and the soft bracket means to exclude it. Infinity, since it's not an actual number, we can't technically include it, which is why it's standard procedure to use the soft bracket, the parentheses. Okay? So there's an example of restricting this guy's domain, because his original domain is all real numbers, right? But we restricted it to x greater than or equal to -4, so that its inverse is a function. Because its inverse was not a function purely, and so we had to cut that off. All right? Now we can dive in with those concepts as our foundation to talking about sine, cosine, and tangent. So this brings us to our first of 3 questions for today. How should we restrict the domain of sine x to make it one-to-one so that its inverse is a function, right? So here's the graph of sine x. You could just stop and think for a moment to yourself, or as I'm explaining this, what do you think would be some good places to, I guess, cut away so that sine x is one-to-one. Now sine is special compared to the parabola, because the parabola just has one place, we called it a turning point that we've learned recently. It only has one turning point and then it comes back up on itself. So we basically just left half of it out and the other half was good. But this one continuously has turning points infinitely forever. So you may have been thinking various places. Now, because it has infinite turning points, there are an infinite number of ways we could technically choose to keep only a piece of this function. But the traditional way has been to keep from here to here. And it makes sense you'd cut off at one of those turning points, because the moment you turn back around a little bit, you're no longer one-to-one. So from here, negative pi over 2, all the way to positive pi over 2 is the only space that we could keep that's near the origin. I guess that's why we've chosen this. And it also helps because it makes sense within the unit circle context. So that sine is still a function. So you'll notice that regular sine, his domain and range, his domain is all real numbers, right? So sine's domain is all real numbers, and his range is from -1 to 1. And I'll use this notation with the brackets, okay? But once we invert him, of course, we've cut some off, so this isn't going to just swap directly, right? Now let's look at this. Graphically, we remember that it flips across the line y equals x, right? Now the line y equals x is going to be not perfectly represented because this doesn't go through that line, but it's going to cause this to go around and flip around like that. And let's just say we have that line more or less here. Then instead, what this guy is going to look like is he's going to come up and then go up like this. Now the graph of him isn't really as special. What really matters is that we lay out his domain and range. So what we're going to do here is we're going to start making a little bit of a library of domain and ranges here. So if I do sine inverse x here, well, this is now switching the role of the domain and range. Remember, we've only kept from negative pi over 2 to pi over 2, right? Well, because we cut this range to negative pi over 2, pi over 2, and sorry, I used the word range. I just meant like the range of numbers. It's confusing that we call it range in the first place, but I cut the domain so we only kept negative pi over 2 to pi over 2, so I've altered that here in my orange. Now what we can do is just switch those two, and this is our domain and that's our range for the inverse function. So I'm going to lay this out. The domain is -1 to 1, and the range is now, this axis will now have the pi halves in it. Negative pi over 2 to pi over 2. And the good thing is you can actually just type this into a grapher or Desmos or whatever, and it will actually show this and display the graph nicely for you to see. So let's dive into looking at cosine and tangent before we finish off for today. So a reminder, with sine, we just looked at the sine graph, decided where to cut the domain, then we reverse the domain and range to figure out the new domain and range for the inverse function, if that makes sense. Okay? So, whoops, I should have labeled this number 3. So this technically would count as number 3. This is one I'll ask you to do yourself. How should we restrict the domain of cosine x and tangent x to make, whoops, bad grammar, to make them 1 to 1. So here's cosine's graph and tangent's graph. You can pause and just think for yourself, where would you cut these so that when we do the inverse, that it is a function, right? So go ahead and do that now. Okay, so we realized for these wavy functions, or when they have the turning point, those are always good places, right? So turning points are going to be options. What we decided for cosine is 0 to pi is what we want to keep. So if we take only these pieces, then the rest of this can no longer be with us. Sorry. And that guy right there is what we keep. Now, I'm not going to draw out the inverse again. By the way, my sign was not very accurate with the numbers in the last one, but I'll leave it to you to actually look at the graph of this. You'll notice that it is the reflection of this piece of the cosine graph across y equals x if you type in cosine inverse x, right? So let's keep record of the domain and range for cosine inverse and for tangent inverse. Now, tangent inverse, you realize, whoops, you realize it's slightly different, but hopefully it's kind of obvious like what we would keep for this once we do the reflecting. Because if we were to reflect all this, you would just have these kind of S shapes stacked on top of each other, and all those things would just violate being a function, so only one of them could be kept, right? And it makes sense to keep only the middle one. So instead of all the different periods of tangent continuing forever, we only keep from negative pi halves up to pi halves for tangent, right? So remember, we've restricted the domain of cosine from 0 to pi, but that is now the range of cosine inverse. So cosine inverse will only ever spit out values from 0 to pi, and luckily the domain is still negative 1 to 1, just like it was for sine inverse, right? Because that was the range of the original function. And I didn't label that here, but there we go. Now for tangent, his range was actually already all real numbers. And if you imagine once you flip them around, or again you can graph it yourself right now, you'll see that once we flip them around, the domain stays all real numbers. So that's nice about tangent inverse. But the range is now going to go, just like sine, from negative pi halves to positive pi halves. So those are the main facts to know from today's lesson, is the domains and ranges for the three inverse functions.